Okay, spring mass system. This part of mechanics of machine will be looking at spring mass system. So the spring mass system here, okay, we have a spring and a mass, and the mass is attached to the bottom end of the spring. So when the mass is released, the mass will be oscillating from point A down to point B, where it reaches its equilibrium position, then back down, further down to point C, and then from point C back to point B, and then to point A. So for the spring, we have a spring stiffness of K. And the spring stiffness K is actually denoted by, the units of K is actually Newton over meter. So here I have K, which is a spring stiffness, is in Newton over meter, and mass is in kg. So for the spring, we have to assume that the mass of the spring to be negligible, and it obeys Hooke's law. So in Hooke's law, it states that the extension or contraction of the spring is directly proportional to the applied force and within its elastic limit. So now consider a mass M attached to the lower end of the spring, causing it to extend by an amount of delta when the mass moves from position A to position B in its equilibrium position shown. So at equilibrium position, we can say that actually the total downward forces, which is due to the mass, we have wave mg. And then the total upward force to be k times delta. Okay, so at equilibrium position, we say that the upward forces is equals to the total downward force. So mg is equals to k delta. So if the mass is now moved downwards through a vertical distance x, that is from position B to C, from its equilibrium position, then the net force is denoted in the diagram as kx. That is the net force. So according to Newton's second law, then the net force should be, we should be taking mg minus the total of k delta and kx. The next part here, as you can see, okay, we have upward force of k delta and kx and downward force of mg. So the deformation, initial deformation of the spring is delta, then to x. So Newton's second law says that net force should be equal to the product of the mass and acceleration. And here we have mg, that is the wave, minus the total restoring forces. So the net force should be equals to mg minus kx plus k delta. And at the same time, the net force can also be equals to ma. Okay, that is the inertial force. So the net force acting on the mass is directly proportional to the displacement of the mass from the equilibrium position. So note that the minus sign here represents that it shows that from the equilibrium position, the force is actually acting in the opposite direction as compared to the displacement of the spring. So the force, the restoring force is acting upwards, where the displacement is measured away from the mean position. So here I have a diagram showing that the spring oscillates from A to B and then to C. And then it will start oscillating from C back to D, and then to E, and then to F, and to G. Then from G back upwards, from G to H and I. Then from I it goes down back to J and K, and after that it repeats continuously unless if there is a frictional resistance by the air. But in this case we have already neglected the frictions due to the surrounding air. So now what I can say is at position A, actually at position A, the displacement of the spring is actually equals to 0. So hence the mass or the wave should be greater. That means the downward force is greater than the upward force, which is directly proportional to the displacement of the springs. And since the spring displacement is equals to 0 at point A, so the downward force, that is the wave, should be greater than the upward force. So that is why the mass moved from A towards C. And then at position C, where the net force is equals to Kx, where mg and k delta has been cancelled out, so it's equals to Kx, which is an upward force, which from here it will bring the mass back to position E. So, and at position E, the same thing happens again, where the deformation of spring becomes 0, and when the weight of the mass is greater than the upward force, so the mass will start moving back to G, and then it repeats to I, and then to K, and it repeats continuously. And is due to negligible surrounding friction. So from here, we also know that Newton's second law from the previous slide, I have already stated that the net force is equals to the product of mass and acceleration based on second law, or Newton's second law. So we have Kx, which is equals to the product of mass and acceleration. So from the previous slide, we know that, okay, Kx equals to ma. So we can manipulate this equation here, and so that it becomes, okay, K over m equals to acceleration over displacement. And from the previous slide, we know that circular frequency, omega, is actually referring to circular frequency. So omega squared is actually equals to acceleration over displacement. So since acceleration over displacement is equal to K over m, so we have the circular frequency now can be equals to K over m. So then we have omega, that is the circular frequency, is equals to the square root of K over m. And also we know that since circular frequency is equals to 2 pi divided by its periodic time, so we can have omega, which is equals to 2 pi over t, and since t, the period time, is equals to 2 pi over omega, and frequency is actually equals to 1 over periodic time, and also we can say periodic time is actually equals to the reciprocal of frequency. So we have frequency is equals to omega over 2 pi. So we can work it out. So we can get frequency equals to 1 over 2 pi square root of K over m. Or you can say that frequency is equals to 1 over 2 pi square root of acceleration over displacement. And also for the period. And frequency here for negligible friction due to the surrounding air, we have what we call the natural frequency. So in equilibrium position, now we are relating it to the equilibrium position. So at equilibrium position, from the previous slide, we know that K delta is equals to mg. Okay, so you can manipulate, so you get K over M equals to G over delta. So, and that is your natural frequency based on G over delta. Now, in the case that we have studied, actually we have already neglected the mass of spring. So if you were to include mass of spring, then in your formula for frequency or periodic time, this denominator here, you should include 1/3 of mass spring mass. Okay, so you must add the mass plus 1/3 of the mass of the spring. So that's all for today. Thank you.